Hey guys, very good evening everyone and welcome to today's session which we are conducting on the domain analytics. We are specifically conducting sports analytics, or rather if I would rephrase, I am specifically conducting the domain analytics for your sports. So from the past few days we have been discussing a lot about various things that we can do in sports analytics pertaining to our data. Today, we will be going a step ahead and we will be discussing about linear regression. So today's agenda is going to be the definition of your linear regression properties. What are the steps for your linear regression? What is the equation? What are the types of linear regression? What are the assumptions? And we will see some of the cases where we can use our linear regression into your sport analysis. Once done with all these, we will be taking a use case where we will be predicting the projected score of a current innings of a cricket match after every 6 overs based on the various factors. Okay. So, linear regression. Linear regression, guys, is one of the easiest and the most popular machine learning algorithms. It is a statistical method that is used for your predictive analysis. So, linear regression analysis is used to predict the value of a value based on the value of another value, two variables. Why? Because the probability associated with a single variable will always be. So we need an interval, or we may need your two variables, always simple. And the summation of probability is always the. So linear regression is one of the easiest and the most popular machine learning algorithm. It is a statistical method that is used for your predictive analysis. Linear regression makes the prediction for your continuous or numerical value. Such as, what are the runs, what are the, runs in the previous over, number of overs, number of balls which have been bowled, so on and. Linear regression algorithm, it shows your linear relationship between a dependent and one or more independent. So you have to vary to avoid. Hence, it is called as a linear regression. Now, since your linear regression shows the linear relationship, which means it finds out the value of a dependent variable is changing according to the value of your independent variable. The linear regression, or the variable that you want to predict, is called as your dependent variable. The variable you are using to predict the other variable's value is called as the independent. For example, it can be used to quantify, linear regression can be used to quantify the relative impact of age, gender, diet on height. Adipose tissue. What is adipose tissue? Adipose tissue is the, deposition of the fat on the abdominal limb. So if there is a sports person and if his waist circumference increases, which means he is having a lot of fat deposit on his abdominal part. Maybe he will not be able to perform in a better manner. Maybe his physical capabilities will be getting hampered. So you find the relation between two variables. If this is increasing, this is increasing. If this is decreasing, this is decreasing. The same goes vice versa. The linearity assumption in linear regression means the model is linear in the parameter, that is coefficient of the variable, and may or may not be linear in the variable. So what happens is the linear regression, it provides a sloped straight line representing the relation between the variables. If I were to give you an image, so let us say so say this is your x-axis, this is your y-axis. These are your data points. These are your data points. And this is your line of regression. Say these are your, this is your independent variable, and these are your dependent variables, dependent variable. So if you observe this image, the formula or the equation we can represent for the linear regression is, I guess I have given that formula over here. Yeah, y is equal to a plus b of. That means nothing based on that image which we are seeing over here. This could be represented as y is equal to a0 plus a1 of x plus error. So y is what? Y is your dependent variable or your target variable. Y is your independent or target variable. This x that you are seeing, this is nothing but your independent variable. Sorry, this is your dependent variable. My bad. So, x is your independent variable. A0 that you are seeing over here, this is the same formula based on the various data points maybe I'm deriving. A0 is nothing but your intercept of the line. A1 is your linear regression coefficient. So, and this E is equal to your random error. The equation has the form of y is equal to a plus b of x, where y is your dependent variable, x is your independent variable, b is the slope or in our case, A1 is the slope and A is your y-term. This is the equation for your linear regression. There are some properties also associated with your linear regression. The line reduces the sum of squared differences between your observed values and predicted. The regression line passes through the mean of your x and y. The regression constant, that is B0, B0, is equal to your y-intercept, the linear regression. These are the properties of your linear regression. What are the steps for calculating or creating your linear regression? Okay. R or Python. So you have to first load the data set into your R of Python. And then you make sure the data meet the assumption. What assumption? That is the point. So these are the assumptions. Linear model makes certain assumptions about the features and the target variable and the relationship when determining the prediction value. These assumptions include that a linear relationship exists between the predictor and the target variable. That is, linearity should be there. There is a normal distribution for every feature of the target. That means multivariate normality should be there. Non-multicollinearity, that is, none of the features are highly correlated to other features. The predicted variables or predictor variables are error-free. The target variables have the same variance in their errors regardless of the values of the predicted mean. So these assumptions should exist when you have loaded the data set. So you need to ensure that these assumptions are exist. Then you perform your linear regression analysis. And then you check for homoscedasticity. Visualize the result using a graph, and then you draw the inference. There are some types of linear regression. One is your simple linear regression. When we talk about simple linear regression, we have one dependent variable, interval or ratio. You people are aware of what is interval and what is ratio. And you have one independent variable. That may be interval or ratio or dichotomy. Dichotomy means differential. Means different. So dichotomy. Sorry for that. Actually, I'm not feeling very well today. Having that stink cough and cold. Another one is the multiple linear regression. In this, we are having one dependent variable and two independent variables. Here we are having one independent variable. Here we are having two independent. When we talk about simple linear regression, if a single independent variable is used to predict the value of a numerical dependent variable, then such regression is called as a simple linear regression. If I were to put into, sentence or in a more meaningful format. When we talk about multiple linear regression, if one or more independent variable, or rather let me rephrase, not one or more, if more than one independent variable is used to predict the value of a numerical dependent variable, then such linear regression is called as a multiple linear regression. Logistic regression. One dependent variable means it is having dichotomous dependent variable and two independent variables. Ordinal, as the name suggests, is having an ordinal value. Multinomial, we are having nominal. And discriminant, we are having normal. So these are some types of your linear regression. There is one more thing that I would like to do. Say this is a y-axis, this is a x-axis. When we talk about linear regression line, a linear regression line or a linear line that shows the relationship between your dependent variable and independent, or a linear line showing the relation between your dependent and independent variable is called as your regression line. And when we talk about regression line, it can show two types of relation. The first one is your positive linear relation. If the dependent variable increases on the y-axis, this is your dependent variable, this is your independent. This is x-axis, this is y. So if the dependent variable increases on the y-axis and independent variable increases on the x-axis, then such a relation is called as a positive linear relation. So for this, your equation will be y is equal to a0 plus a1 if the dependent variable decreases on the y-axis and independent variable increases on the x-axis, this is called as your negative linear relation. The formula for negative will also be same, but with a minus. Right? Now, let's see what else we are having. Okay. So when selecting the model for the analysis, an important consideration is your model. Adding independent variables to a linear regression model will always increase the explained variance of the model, which is actually expressed as your r raised to the power 2, Rf. However, overfitting can occur by adding too many variables to the model, which reduces your model generalizability. Occam's razor theorem. What is Occam's razor theorem? Occam's razor theorem states that the model should be into its simplest form. And so says your principle of parsing. So Occam's razor describes the problem extremely well. A simple model is usually preferable to a more complex model. That is what your Occam's razor theorem. Statistically, if a model includes a large number of variables, some of the variables will be statistically significant due to chance. Then, what are the parameters of best fit line? That also remains a question. When working with the linear regression, the main goal is to find the best fit line. That means the error between the predicted value and the actual value should be minimized. The best fit line will have the least error. The different value for the weight or the coefficient gives a different line of regression. So we need to calculate what the best value for A0 and A1. What is A0 and A1? These are nothing but your coefficients of the line. When you will find or when you will do the calculation for this, you will find the best fit of the line. To find this, we use a function called as a cost function. Then we have something called as a gradient descent. Gradient descent, guys, is used to minimize the MSE, that is mean squared error, by calculating the gradient of your cost. The regression model uses a gradient descent to update the coefficient of the line by reducing the cost function. And how it is done? It is done by a random selection of values by coefficient. Sorry. And then iteratively updating the values to reach the minimum cost function. Oh. While some of the assumptions, again coming back to the assumptions, what were the assumptions that we discussed? Linear model makes certain assumptions. A linear relationship should exist between the predictor and the target variable. Means there should be linearity or multivariate normality, so on and so forth. Various assumptions we saw few moments. While some of these assumptions are unrealistic and practical, there are some regression methods, such as your weighted, generalized, and partial least squared methods, that are able to handle the errors that may arise from these. So we need to keep that thing also in. So if I were to summarize it, linear regression attempts to model the relation between two variables by fitting a linear equation to observed data. One variable is considered to be an exploratory variable and the other is considered to be a dependent variable. Let's say, for example, a modeler might want to relate the weights of individuals to their height, right? Using a linear regression. Before attempting to fit a linear model to observe data, modeler should fit determine, maybe, even if we talk about the sports person. For a sports person, also the height and all these things matter. So the modeler should first determine whether or not there should be a relationship between the variable of input. This does not necessarily imply that one variable calls for the other. For example, high status score does not cause higher college grade, but that there is some significant association between the two variables. Using the scatter plot, it can be helpful to determine the strength of the relationship between the two variables. If there appears to be no association between the proposed explanatory and dependent variable, that is the independent and dependent variable. If we talk about our terms, what we discussed, that is the scatter plot does not indicate any increasing or decreasing trend, then fitting a linear regression model to the data probably will not provide a useful. Clear that thing in your mind, hammer that thing. A valuable numerical measure of association between two variables is your correlation coefficient, which is nothing but a value between your -1 and indicating the strength of the association of the observed data for your two variables. This is how we can summarize the linear. Talking in terms of our sports analysis, we might want to predict the attendance to some game based on the different predictions. That is, the quality of the team, of the opponent, size of the market, date of the event, others. If I were to say, if there's a cricket match going on, assume that. Various parameters are there, various variables. So if a match is between India versus Pakistan, oh my God, that is going to be a, very great. People will be going bonkers. Right? Everyone wants to see that. Only if this match maybe is happening in Asia. But if this match is happening somewhere rather than Asia, you cannot expect the same kind of audience that you would, get, say, or rather Asia, if I were say that maybe in Delhi or maybe in Lahore. If the match is happening in Delhi and Lahore, even, people will, the capacity of the stadium will be getting choked. Various variables are there, and you find the relation. If the same match is happening, say, in another country, maybe in South Africa, the kind of audience or the number of audience that you expect at these venues, you can't expect in South Africa. Based for this fact, I'm talking about this. Maybe if a match is between South Africa and Australia, and the match is happening in South Africa, then you will again, have a good audience. So it depends upon variable to variable how you find the relation and what relationship is working, right? Because we want to be able to maximize the ticketing profit, or we want to estimate the adequate size of a new one. The same example. Linear regression is a precious tool for your sports analysis. And indeed, running a linear regression on some data can allow the practitioner to detect correlation between variables and especially select variables which are more susceptible to explain the observed risk. For instance, one might discover that actually the date of an event is much more influential on the attendance than the quality of the team, which gives insights of the necessary actions to be taken. Say India versus Pakistan match is there on Monday. The kind of audience at say 11 a.m. The number of audience you get at this time will be definitely low when the match is on Sunday, say at 7 p.m. So it gives the insights to the necessary actions to undertake. In other terms, the goal of running a linear regression model can be to rationalize some decisions with your quantitative strategy. That is all about our linear regression and its uses in your, sport term. So what all things we discussed till now? We discussed what is the definition, what is the meaning of your linear regression. We discussed about the property, what are the steps for your linear regression, what is the equation that we use. I mean, you should know about the equation, though you are not going to do anything, manually. But again, you should be aware of like what things are happening in the back. Types of linear regression we saw, assumptions we saw, and we saw that in sports analytics for what purposes can we use our linear regression. Now, let me take you to my Jupyter notebook. Okay. And this is it. I've imported my required libraries over here. Then I've loaded my dataset. When I said data.head, it is going to show me your top 5. When I say data.tail, it is going to show me my last 5 options. I wanted to find out about the shape of my data. How many rows and columns I have. So I said data.shape. It is giving me 32,170, rows and 18 columns. So here you can. The last number is always, ignored in the Python. We all are aware. I wanted to know the data type. So again, data.data. When I said data.describe, it is giving me by count, mean, standard deviation, minima, maxima, all. Now I am using my all features. Means I'm using for descriptive statistics, I'm using my all categorical. So I'm saying data.describe include is equal to 1, and these are the categorical data which I was. Then I started with your data prepare. First, I tried to find out whether there are missing values or not. Then I check for my duplicate values. Based on some inferences, I assume that I don't need few calls. That is unnamed extras match ID runs all. Extras I didn't need it. I means few of the columns I was not deeming to be, used. So I just dropped that. And then I got my 14 columns. Data.in. Now I'm converting my categorical values to a numerical value. For that, I am importing my labeling. Once that is imported, I am saying that use your label encoder on venue, batting team, bowling team, means on the categorical data which I have. batting team, bowling team, venue, all other categories. So I'm using my label encoder to convert my categorical values to numerical values, and I have the data. So I said, from the data, take the column D, which I have already initialized in a parameter called as variable called as COLS, which means column. I am saying apply label encoder dot fit underscore transform. Whenever you say dot fit, your model is start run. The values which I get, I am storing it into the same data set into your COLS. Now, again, I am saying data dot head, it is giving me my top 5 observations. Now I'm saying from the IP, from the data set name data, use your venue, batting team, bowling team, striker, non-striker, and bowler. Take this column and store it into a variable called as IPL data. So this is how my IPL data set is. Now, I am taking my IPL data set index location. I am taking all the rows and all the columns. So when I say X, and I am storing it into a variable called as X. So when I say X, I have all my rows and all. Whenever you have this kind of thing, the first value depicts your row, second depicts your column. When you are having null value, means you are taking all rows and all. Now, I am saying data.y. I am taking my data set. I am saying data.y, store it into a variable called as, and when I say y, I have the value. Name is y. Length is your 332,178. Obviously, we are having that many rows. Data type is your float. What happens? I am taking this from my data set data, and I am storing it into a variable called as your. Now I am starting with my model building. For that, I am importing my train test script from sklearn.model underscore selection. Testing size, I am taking as your 30%. So training data will be your 70%. Initialize two parameters over here. And when I say give me the shape of my training data, so it is giving me 20. How many we are having? 32,170. Out of this, we have taken 70%. So it will be something. And your 30% will be your testing. I want to scale the data, so I am importing a standard scaler, and I'm using this on my training and testing data both. After transforming my training and testing data, the scaled value which I am getting, I am storing it into x underscore train and x underscore. I am importing my linear regression over here from your scalar.linear underscore model. And I say whenever I say a word or use the word multilinear, it should perform my linear. So I am using my multilinear, which is nothing but your linear regression. I am running that model by dot fit on my training data. Then I am getting my predicted values on my testing data. From sklearn.metrics, I am importing my r raised to the power 2 underscore is 4, r2 underscore and mean squared error. I'm using that on my testing data and predicted value, which I calculated over here. The values which I'm getting, I'm storing it into R2 variable, which is nothing but 17. I am also trying to find out the square root. After getting the mean squared error from my testing and predicted value, first I'm getting my mean squared error, then I'm getting the square root of that. So this is what I'm. So this is how, guys, you perform your linear regression when we talk about your post analysis. Again, these codes I will be sharing with you people. Maybe by tomorrow. Tomorrow we are having the last session. So tomorrow I'll be sending you all these codes on your mail ID. Raksha and other participant of our Lugi Bombay side the Bona. If you people want, then you can share your email ID in the chat window, and I'll be forwarding the dataset and the codes by tomorrow. After this session ends tomorrow, so most probably by day after tomorrow, you people will be getting the codes and the dataset for your further. Okay. So guys, this is where I'm going to wrap up this session for today. Thank you so much for joining, guys. Yeah. And see you tomorrow. Thank you.